Hey everyone, welcome back to Everything is Relative. I'm Mr. K, and today we're going to be doing more topical past paper questions on the topic of nuclear physics for Cambridge A-level physics. Now, these are Papa Cambridge questions, and I leave a link to the website from which you can download these questions. They are good questions to attempt before you watch these videos, and they will help you get an understanding of what questions can look like in your examination in a few months. Now, the topic as it's labeled by Papa Cambridge is particle and nuclear physics, but it's actually just nuclear physics. It's paper 4, it's A-level physics. Particle physics is its own topic in AS physics, but we're just going to look at the nuclear side of things. And we're going to look at questions 397 to 405 as they've numbered them. So if you're using these documents, they are quite helpful. These questions are already put together and there's answers as well, so it's easy for you to have a set of questions that you can work with topic by topic. And nuclear physics is one of those topics that's novel for most people studying A-level physics. So the first question, and again it's not clear, so I'm just going to write the question out on top. This is question 397, and the subject code, like always for physics, is 9702. This is the exam from summer 2020, so that's May-June 2020. And this is question paper 4, variant 1, and this is question 11 from that paper. Now we are told that an electron at rest has mass me and charge minus q. A positron is a particle that at rest has mass me and charge plus q, the positron being the antiparticle of the electron. Now a positron interacts with an electron. The electron and positron may be considered to be at rest. The outcome of this interaction is that the electron and positron become two gamma ray photons, each having the same energy. We are told then to calculate for one of the gamma ray photons the photon energy in joules. So what happens? Well, when a particle meets its antiparticle, in this case an electron and anti-electron or positron, they will annihilate each other and they will emit radiation in that process. So let's assume I have an electron and I have a positron. They're moving along. Well, actually, they're not moving. They're relatively stationary. Actually, they are stationary. And they collide. And you don't need to know this Feynman diagram. I'm just drawing a diagram so that you can understand what happens. But they will destroy each other. The mass that existed before is now converted into energy, and it is the energy of two gamma ray photons. So mass disappears, energy appears, but E is equal to mc squared, and so all is well with the universe. And so two massive particles collide, annihilate each other, and release two massless particles. And we want to know the photon energy. Well, now there's two particles going in and there's two gamma rays coming out. So I can say 2mc squared is equal to, well, 2E. But I can simply see that the energy of a single photon is going to be mc squared. It's the energy of either the positron or the electron. And I know the mass of an electron, if I go to my data sheet, to be 9.11 times 10 to the minus 31. Be very careful about writing the value for the atomic mass unit. The mass of the electron is much smaller. Times c, the speed of the electromagnetic wave, 3 times 10 to the power 8 squared. And so I'm seeking an answer in joules, and what I get is 8.2 times 10 to the minus 14 joules, which I would expect a very small value. And so to two significant figures, this number doesn't change. 8.2 times 10 to the minus 14 joules of energy for a single photon. I'm asked for the photon energy, not for the total energy of the two photons. So just be careful when reading the question. And it also says for one of the gamma ray photons, very specific. We're also asked to calculate for one of the gamma ray photons the momentum. Now, momentum of a photon is very different. We can't use the equation mv because photons have no mass. But we can use the equation P is equal to E over c. Well, this is fine. I need the momentum in SI units, Newton seconds, and I have the energy already in SI units. 8.2 times 10 to the minus 14 joules divided by the speed of light, 3 times 10 to the power 8. And what I get is, again, a very small value, 2.73 times 10 to the minus 22 Newton seconds. Or to two significant figures, 2.7 times 10 to the minus 22 Newton seconds. We'd expect the momentum of a single photon to be low. It is low, and hence photons don't do a lot of pushing, but if there are many of them, they can have a push that is still significant. And so, yes, photons have momentum. They can physically cause a force on an object. The last sub-question says, state and explain the direction relative to each other in which the gamma ray photons are emitted. Okay, so how do we go about this question? And this is kind of a tricky one. But what we remember, at least from our AS physics, is that momentum must always be conserved. So how do we conserve momentum in this system? Well, we know that the initial momentum of the electron and positron is 0. So it's 0 before, I'm going to use the word interaction instead of annihilation because I don't think I could spell annihilation right now. So I'm going to say before interaction. Now, since the momentum must be conserved before and after the interaction, the gamma ray photons must move in opposite directions. They have to move opposite to each other. They must move in opposite directions. Now, why am I saying this? Well, think about this. Initially, the electron and positron have no momentum, so the initial momentum is 0. If I want the final momentum to be 0, but I know I'm producing 2 gamma ray photons that I'm moving off, remember, electromagnetic radiation must be moving at speed c. The only way to conserve the momentum is if one is moving in one direction and the other is moving in the totally opposite direction, because momentum is a vector that have the same speed in the opposite direction, so the total momentum will be 0. And hence, momentum before is 0, momentum after is 0, momentum is conserved. So whenever you get this kind of question, it's a kind of question that will come up when you study positron emission tomography, PET scanning. And you are expected to understand why gamma ray photons are emitted in opposite directions and they have equal energies. This is to conserve momentum before the interaction and after the interaction. And so that's a common type of question that you should have seen at some point before. But it's a very clever application of the conservation of momentum. Now the next question is as numbered, question 398. And this again, 9702 from summer 2020. So again, if you want to find these questions individually, to tackle them individually, then you can do that by using these question numbers. It's question paper 42 from summer 2020 and question 12 from that paper. And the first thing they ask us is to state what is meant by the mass defect of a nucleus. And again, you know that there's multiple answers that you can provide here. So what does the mass defect tell us? Well, the mass defect tells us the difference in mass between a nucleus, when all the nucleons are brought together by the strong force and held together in the nucleus, and the constituent nucleons when they are out of the nucleus. So how do we write this concisely? We can say it is the difference between the mass of a nucleus and the mass of its constituent, I think that's correct, constituent nucleons, that is protons and neutrons, specifically when the nucleons are out of the nucleus. Or what I can say to be more correct is when the nucleons are separated to infinity. When I say separated to infinity, what do I mean? It means that the nucleons are outside the nucleus. So it's a difference between the mass of a nucleus and the mass of the components when we take those components out of the nucleus, when we completely remove them from the nucleus. And it turns out those two masses are not the same. So the mass of a nucleus is always less than the sum of the masses of all the neutrons and protons that make that nucleus. And that's because of the strong force. So that is, they only asked for mass defect. And that's what we mean when we say mass defect. Now the next question says some masses are shown in the table. And we're given the mass of a proton, a neutron, and the helium-4 nucleus. And you probably know where this is heading. But the first question says, show that the energy equivalence of one atomic mass unit is 934 mega electron volts. Now, for many of you, there may be multiple different ways in which you want to do this. I always go with the equation E is equal to mc squared, and I put the mass of one atomic mass unit into that equation. So that's 1U multiplied by 1.66 times 10 to the minus 27 kgs for every atomic mass unit. This you get from your data sheet. You know that one atomic mass unit is 1.66 times 10 to the minus 27 kgs. And c squared, as always, is 3 times 10 to the power 8 meters per second. And all of that is squared. And so what we get here is 1.49 times 10 to the minus 10 joules, which is great, but the answer is expected to be in mega electron volts. So I need to divide this by 1.6 times 10 to the power minus 19 times 10 to the power 6, or simply times 10 to the minus 13, because I'm asked for mega electron volts. And that's joules for every mega electron volt. And you can see the joules will cancel, and what I'm left with is an answer that should be 934 mega electron volts as required. And so this is, again, there are multiple ways of doing this. I just feel comfortable using E is equal to mc squared and throwing in the value of one atomic mass unit. That should, when I convert to mega electron volts, give me 934. Next, we are asked to show that the binding energy per nucleon of a helium-4 nucleus is 7.09 mega electron volts. Well, they asked us for the binding energy per nucleon, but we can start by just calculating the binding energy. Now remember what binding energy is. Actually, first, remember that the helium-4 nucleus is He42. 2 protons, 2 neutrons, that is 4 nucleons in total. It's delta m c squared. It's the mass defect times c squared. And there's probably a reason why they asked us to show that 1U is 934 mega electron volts. And so all of these masses that I'm given are in atomic mass units. So instead of converting them to kg, I can use atomic mass units and then use my value of 934 as c squared, which is just an easier way of doing this calculation. Now, the mass of the constituent components, there are 2 protons. So that's 2 times the mass of each proton, 1.007276. I'm just going to use the masses as given. Plus, there's another 2 neutrons. That's 2 times the mass of a neutron, 1.008665, minus the mass of the entire helium-4 nucleus, which is a smaller number, 4.001506. And all of this needs to get multiplied. So now that's the mass defect in atomic mass units. Now I need to multiply the energy equivalent of 1U is 934. So I multiply all of this by 934. And this will give me a binding energy in mega electron volts. So I get 284 mega electron volts. But I'm asked for the binding energy per nucleon. And so the binding energy per nucleon is simply this number, 284, divided by the number of nucleons, which is 4 for helium-4. And what I get is what I've been asked to find, 7.09 mega electron volts. Actually, that wouldn't give us 7, would it? It's 28.4 mega electron volts, not 284. That number's way too high. So 28.4 mega electron volts divided by 4 should give me 7.09 mega electron volts per nucleon. So that's the amount of energy I would require to remove each nucleon individually from the nucleus, and it gives us an idea of stability. We are then told in part C that isotopes of hydrogen have binding energies per nucleon of less than 3 megaelectron volts. And we are to suggest why a nucleus of helium-4 does not spontaneously break down to become nuclei of hydrogen. So there's a few possible answers, but the one that makes the most sense is if you look at the binding energy per nucleon, we know that there's a relationship between the binding energy per nucleon and stability. Now, the binding energy per nucleon is not just higher for helium-4 than the hydrogen isotopes, which are around 3 megaelectron volts, but much higher. So the binding energy per nucleon is higher in the helium-4, than the hydrogen isotopes. So why would helium spontaneously break down if it's going to have a lower binding energy per nucleon and become inherently more unstable? So what does this mean? It would require a large amount of energy to separate the nucleons to infinity. Separate its nucleons. And so the binding energy per nucleon for helium is much higher than hydrogen. So we'd require a lot of energy to split the helium and make it into an isotope of hydrogen. And so that's the reason why it would not spontaneously, the question did ask very cleverly, spontaneously. So helium-4 is not going to spontaneously break. Spontaneous means without any encouragement from the environment, without any other factors occurring. It's not going to break and become something less stable. So with energy, yes, it's possible that helium could become hydrogen, but spontaneously this will not happen. Things with higher binding energies per nucleon will generally not tend to spontaneously become things that have a lower binding energy per nucleon. Remember, everything in the universe is trying to tend towards a semblance of stability. And so that was an 8-mark question. Again, a mix of calculation and understanding of the concepts and the topic itself. Now the next question is question 399. Actually, not 399, but 400. So 399 is a repeat question. Some of the questions are repeated, so you'll notice I skip some of the questions and go on to the next one that's novel. But we are told that the incomplete, actually no, before we do that, let me write this question number down. That's the March exam from 2019, M19, question paper 4, variant 2, and this is question 12 from this paper. Now we're told that the incomplete nuclear equation for one possible reaction that takes place in the core of a nuclear reactor is given as follows. And we are first told to state the name given to this type of nuclear reaction. So let's see what's happening. We have uranium-235 being struck by a neutron. The uranium-235, as we know, then becomes uranium-236, which is unstable, and the uranium-236 undergoes nuclear fission. In the process, we have daughter nuclei that are formed and some neutrons. In this case, the daughter nuclei are lanthanum-139 and molybdenum-95, and 2 neutrons. And so, because a heavy, unstable nucleus like uranium splits into smaller, lighter nuclei, this reaction is nuclear fission. Please remember the spelling of fission and fusion is important. You shouldn't have one S in fission, nor should you have 2 S's in fusion. So make sure you understand the spelling, because it's easy for a marker to not be too certain. If you write fission with 1 S, it looks like fusion and might be marked wrong. The next part of the question says complete the nuclear equation. Now we know why the dotted line was there. Okay, so let me look at the numbers. So the numbers on top, which are my atomic numbers, my mass numbers. I have 236 on the left-hand side. On the right-hand side, I have 236. So my mass numbers are fine. Don't have an issue with the mass numbers. The mass numbers balance. Let me check my atomic numbers. The atomic number Z on the left-hand side is 92. That's 92 plus 0. But on the right-hand side, I have a much bigger number. 57 plus 42 is 99. And so I have a difference of 7 on the right-hand side than I do on the left-hand side. So I have to make the right-hand side equal the left-hand side. Now, it's a bigger number, so there needs to be a negative. And there needs to be 7 negatives. Now, the only thing I know that's going to be 7 negatives is 7 beta particles, or 7 electrons. And now the values for Z, the atomic numbers, will balance on both sides. So this nuclear reaction, this nuclear fission, releases 2 neutrons, which can then go on and excite further uranium atoms, but it also releases 7 beta particles. So it is a highly radioactive process. It's a process by which a huge amount of radiation is released. We are then told that the mass defect for this reaction is 0.223 U. Calculate the energy in joules equivalent to this value. Well, Einstein's equation, E is equal to mc squared, will get us there. And this is a mass of 0.223 U multiplied by 1.66 times 10 to the minus 27 kgs for every atomic mass unit. Converting this to kgs, and now we can multiply this by c squared, which is 3 times 10 to the power 8 squared. And what do we get? We get an energy that's 3.33 times 10 to the minus 11 joules. So what this means is the amount of energy released in this interaction is not a lot, actually. It's 3.33 times 10 to the minus 11 joules. When I say not a lot, I mean this is for a single one of these reactions. But we remember, we never ever have one of these reactions happening in isolation. We have billions or trillions of them happening, which is why the energy ramps up very quickly. Now, we are told to suggest 2 forms of the energy that is released in this reaction. Now, there are a few forms of energy, and 2 of them are as follows. So the first form that this energy is released in is the kinetic energy of the products. Remember, beta particles travel at 99% the speed of light, and so they get a significant amount of kinetic energy from this reaction. And so the first form of the released energy would be kinetic energy of the products. The second form of energy, which we actually don't always see in the reaction equation, would be the possible emission of gamma particles. So it's possible that this reaction also releases electromagnetic energy in the form of gamma rays or gamma radiation. We don't really need to see the gamma in this equation because gamma doesn't have an atomic number or a mass number. But it's possible that gamma radiation is released in this interaction, and so we have beta and gamma particles, making this a highly radioactive event. And so these are 2 possible forms of energy that is released in this reaction. Again, if we multiply this energy by many particles, it becomes a large amount of energy, which is why nuclear fission releases huge amounts of energy. The problem is, obviously, these radioactive products that are formed and also the radioactive particles that are emitted. So lanthanum and molybdenum are both also radioactive. And so you can see why this is not always the best option for generating power. But that was a 7-mark question in total. So not a very long question, but it was still worth a significant 7 marks. Now the next question, oddly enough, the next question is very similar to the one we've just answered. And this is question number 401, as it's numbered in the Papa Cambridge question paper. This is from winter 19, that's November-December exams 2019. Question paper 4, variant 1, and question number 12 from that paper. And we are given the same reaction that we've seen before. Uranium-235 plus a neutron gives molybdenum-95 plus lanthanum-139 plus 2 neutrons plus 7 electrons. So we actually can see that our answer from the previous first question was correct. We're then given a whole lot of data, and we are told that here's the data for the mass in atomic mass units for molybdenum, lanthanum, and uranium. We're given the total mass of the separate nucleons, the mass defect, and so we don't have to calculate the mass defect, it's done for us, and the binding energy per nucleon. And the first thing they ask us to do is, guess what? To show that the energy equivalent to a mass of 1U is 934 mega electron volts. So what am I going to do? I'm going to do what you can't do in an exam, which is copy and paste. If I'm allowed to do that, I'm probably not allowed to do that. So your lucky day, I'll do this again. E is equal to mc squared. We'll never forget it now, that's for sure. So I use Einstein's equation and throw in the value of one atomic mass unit, multiply this by 1.66 times 10 to the minus 27 kgs for every atomic mass unit, multiply this by 3 times 10 to the power 8 all squared, and then I'm going to divide this by 1.6 times 10 to the minus 13 to get my answer from joules to mega electron volts. And guess what? I get this to be 934 mega electron volts. Now you see I've done many steps in one. You don't need to do this. You can do this mathematics step by step to find that one atomic mass unit has the energy equivalence of 934 mega electron volts. We're then told to use data from the figure to calculate the binding energy per nucleon of a nucleus of uranium-235, basically completing the table, filling in the dotted line of the table. What's the binding energy per nucleon? So the binding energy per nucleon is the energy equivalent of the mass defect. Delta M times C squared is the energy equivalent of the mass defect for uranium-235 divided by the number of nucleons, the nucleon number A, the mass number. And so this is 1.865. Where do I get this number? This is the mass defect for uranium-235 multiplied by C squared, which is 934, divided by 235, since there are 235 nucleons in uranium-235. And what I find is the binding energy per nucleon is 7.412 mega electron volts. And so if I fill in the table, I'll write this as 7.41. I can write two significant figures, 7.41 mega electron volts. And they didn't give me a unit in this question because they wanted me to fill in the figure. So I had to infer that the unit I needed to use was mega electron volts. Hence, I multiplied my mass defect by 934 and not 3 times 10 to the power 8 squared. And so the binding energy per nucleon of uranium-235 is 7.412. Now we are told next that the nucleon number of an isotope of the element rutherfordium is 267. When we want to state whether the binding energy per nucleon of this isotope will be greater than, equal to, or less than the binding energy per nucleon of uranium-235. Immediately, we can see that rutherfordium here has a higher mass number, 267. And what we know from our graph of nucleon number or binding energy per nucleon against nucleon number is that heavier elements than uranium towards the right have a lower binding energy per nucleon. They are less stable. So rutherfordium will be less stable than uranium-235. And so the binding energy, they didn't ask us to explain, they simply asked us to state. So the binding energy per nucleon, which is an indication of stability, will be less than that of uranium. They simply said state, they didn't say explain. And it's less than that because it's less stable. lower binding energy per nucleon. Next we are told to calculate the total energy in mega electron volts released in this nuclear reaction. So how do we find the total energy? Well, the total energy is simple. I take the binding energy of the products and I subtract the binding energy of the reactants. So if there's a difference in energy, that energy is released, and it's released in the form of kinetic energy. It's given to electromagnetic radiation, etc. And it's the thing that makes this reaction dangerous and so on. And so what is this? It is the total binding energy of the products, which is the 95 molybdenum nuclei times the binding energy per nucleon for molybdenum, 8.443. Where do I get this? I get this from my table. Molybdenum 95, binding energy per nucleon 8.443. And then I do the same for lanthanum. Remember, the binding energy of the reactants will always be higher than the binding energy for the product. Plus 139 for lanthanum times the binding energy per nucleon, 8.189 minus 235 nucleons of uranium-235 times 7.41 mega electron volts per nucleon. And what I get is an energy of 199 mega electron volts. And so this may not seem like a large amount of energy. Indeed, for a single reaction, it is quite large. On the grand scale of things, it may not be. However, we generally don't have a single atom of uranium undergoing fission. We generally have millions and billions and trillions of them, so the energy does scale up quite rapidly. And this next question actually shows us this. We are told that the nuclei in 1.2 times 10 to the minus 7 moles of uranium-235 all undergo this reaction in a time of 25 milliseconds. And we want to find the average power released during the time of 25 milliseconds. So how do we know the power? Well, let's forget about the power and let's first think about the energy, the total energy that's going to be released. We know the energy that's released for a single nucleus of uranium. Now we want to find the number of nuclei in this many moles of uranium. So we think back to ideal gases. Number of nuclei, N, is the number of moles, N, little n, times Avogadro's number, Na. And the total energy, I'll call it ET, will be 199 multiplied by this number. So it is the energy that we calculated before for a single nucleus times the total number of nuclei. And hence the power, I'm going to try and do everything at once now, is this energy, 199 times little n times Na, the total energy divided by the total time. Remember, energy divided by time is power. And time is given as 25 times 10 to the minus 3 seconds, 25 milliseconds. Now, if I throw all these values in, I get 199. Now, again, I have to be very careful. I have to make sure I convert this to joules because I'm given watts in the answer. So I multiply this by 1.2 times 10 to the minus 7, that's the number of moles, times 6.02 times 10 to the power 23. And I have to convert the mega electron volts to joules, so I multiply this by 1.6 times 10 to the minus 13. Minus 13 because this is mega electron volts, not simply electron volts. And then I divide all of this by the time, 25 times 10 to the minus 3 seconds. And what I get is 9.2 times 10 to the power 7 watts. Or to two significant figures, 9.2 times 10 to the power 7. So you can see it is a significant amount of power. And we only needed 1.2 times 10 to the minus 7 moles of uranium-235 to achieve huge amounts of power. So 92 million watts, 92 million joules of energy every second. And so now you see why nuclear fission is powerful, but also can be highly dangerous. Now the next question is question 404, and this is from the winter 2018 paper, specifically question paper 4.1, and this is question number 11 in that paper. We are told that a stationary isolated nucleus emits a gamma ray photon of energy 0.51 mega electron volts, and we are asked to state what is meant by a photon. Now, if you've seen my previous video on quantum physics, this question will be kind of boring for you, but it's a quantum, or you can say a packet. I prefer the word quantum, it's more formal. It's a quantum of energy that specifically is in the form of electromagnetic radiation. So a quantum of energy in the form of electromagnetic radiation is referred to as a photon. So a little bit of going back to quantum physics, you can see that the topics will always be linked. I mean, physics is physics, science is science. And we're told that for the gamma ray photon, we are asked to calculate the wavelength. Well, what do I remember? I remember that the energy is hc over lambda, Planck's constant times the speed of light divided by the wavelength of that photon, which means the wavelength of the photon lambda is hc divided by E, which I can write as 6.63 times 10 to the minus 34 multiplied by the speed of light c, 3 times 10 to the power 8. Now there is a single value for hc in terms of electron volts that you could calculate, electron volt nanometers, but I wouldn't suggest remembering an extra piece of information. Divide it by 0.51 mega electron volts and convert this to joules by multiplying it by 1.6 times 10 to the minus 13. And so I get a wavelength in meters of 2.44 times 10 to the minus 12 meters. Very short wavelength, and hence this is a gamma ray photon. So in two significant figures, this is 2.4 times 10 to the minus 12. Now they ask us for the same gamma ray photon to find its momentum. Remember, momentum for a photon, P, is E by C, which is hc over lambda over c. hc over lambda c. Hey, that simplifies to hc over lambda, or rather h over lambda, which is again Planck's constant, 6.63 times 10 to the minus 34. But guess what? I know the wavelength, I've calculated it. 2.44 times 10 to the minus 12. And what I get is 2.72 times 10 to the minus 22 Newton seconds. So again, it's not a very significant momentum, but it's not zero. And so this gamma ray photon has a momentum of 2.7 times 10 to the minus 22 Newton seconds. Now the question is not done. The next part of the question says, for this nucleus, determine the change in mass delta m during the decay that gives rise to the energy of the gamma ray photon. Well, what I know is that E is this mass defect delta m times c squared, this change in mass, and so this change in mass delta m is the energy of the photon divided by c squared. I have to lose this mass somewhere in the universe to be able to get the E somewhere in the universe. And so this E, again, is 0.51 mega electron volts. We'll convert this to joules, multiply by 1.6 times 10 to the minus 13 over 3 times 10 to the power 8 meters per second squared. And what we get is 9.07 times 10 to the minus 31 kg. or 9.1 times 10 to the minus 31. Very familiar looking mass. It looks like an electron has been lost somewhere in the universe for this gamma ray photon to be emitted. We've seen the first question that we've done. This is identically the process. Electron and positron will collide and annihilate each other and give off two gamma ray photons. We're then asked to explain why after the decay the nucleus is no longer stationary. So this stationary isolated nucleus emits a gamma ray photon at some random time. The nucleus fires the gamma ray photon with a certain energy and a certain momentum in a given direction. If it's initially stationary, it can't be stationary because it's fired off a photon, a gamma ray photon. And like we've said before, momentum must be conserved before and after the photon is fired. So the nucleus must recoil or must move in the opposite direction to the photon, and this will conserve momentum. So since momentum must always be conserved, the nucleus has to move in the opposite direction to the photon, similar to a cannon firing a cannonball. Initially, the cannonball are both stationary, but after the cannon fires the cannonball, they both move in opposite directions, and momentum before and momentum after are both zero, hence momentum is conserved. So a very good, again, another good application of the conservation of momentum here all the way in nuclear physics. The next question is numbered 405. And this is from the winter exam of 2018. That's November, December, and this is from question paper 4, variant 2, and this is question number 12 from that paper. And we are asked, firstly, to state what is meant by nuclear fusion and nuclear fission. And so you don't need all of the space, you don't need a very long explanation, but what is nuclear fusion? Well, it is when two light nuclei combine to form a single heavier, let's just say a single nucleus. So two light nuclei combine to form a single nucleus. Simple. Seems quite straightforward, actually. Nuclear fission, they didn't say spontaneous or induced nuclear fission, they simply said nuclear fission. So nuclear fission is a large nucleus that splits to form smaller nuclei. So they're basically the opposite processes. And I don't really need a lot to describe either. You could go into more detail. There are many lines for you to do that. It's not really required, but you could go into more detail about fusion, fission, both of these processes releasing energy, the daughter products in fission being roughly half the size of the parent nucleus, whatever. But this is the idea between fusion and fission. This is what we mean when we say fission and fusion. Now the next question says a nuclear reaction, which may in the future be used for the generation of electrical energy, is given here. This is nuclear fusion. So deuterium and tritium are fusing to form helium-4 and something else, and we want to know what this particle X is. Well, if I immediately look at the atomic numbers are fine, but the mass numbers are not. I have 5 on the left-hand side and 4 on the right-hand side. Now, I'm very good at mathematics, so I know that 5 is 4 plus 1. So I need something with a nucleon number of 1, but a proton number of 0. Well, that thing is a neutron. So X on the right-hand side will be a neutron 0, 1, and that balances the equation. So a fusion reaction can also release a neutron. We are then given data for the binding energy per nucleon of some of the nuclei, that is deuterium, tritium, and helium, the binding energy per nucleon for each of them. and we want to know the binding energy per nucleon of X. So how do we find the binding energy per nucleon of X? Well, X is a neutron. Well, a single neutron can't have a binding energy, right? A binding energy, remember, must be for an entire atom. Single nucleon that's free is not in a nucleus and hence doesn't require any energy to be separated from the nucleus. So this neutron is a free neutron. There's no energy required to separate it from a nucleus because it's not in a nucleus. It's not being held by the strong force. So the binding energy per nucleon of X is actually 0, hence just the dotted line and no space to do a calculation. We're then told to calculate the energy change that takes place in this reaction. Now, like always, we have to find the total energy, delta E, but we are actually given the energy per nucleon. So we have to multiply this energy per nucleon by the number of nucleons. So the energy change is the 4 nucleons in helium-4 times that energy per nucleon, 11.3290, minus the binding energy per nucleon of the reactants, deuterium and tritium, 2 into 1.7813, because there are 2 nucleons of deuterium, minus 3 nucleons of tritium into its binding energy per nucleon, 4.5285. And we have to be very careful. These are all in joules, and they are specifically times 10 to the minus 13 joules. So we have to multiply all of that by 10 to the minus 13. And what we get is 2.82 times 10 to the minus 13 joules. We can keep this answer to 3 significant figures, 2.82 times 10 to the minus 13 joules. So that's the energy change that takes place in this reaction. That's the energy released for a single fusion reaction. Again, it doesn't seem like a lot of energy, but it is a lot of energy when we have multiple of these tritium and deuterium atoms undergoing fusion. And this next question will show that. We're told to use our answer in part 2 to determine the energy released when 2 grams of deuterium reacts with 3 grams of tritium. But wait a minute, what do I know? Deuterium has a mass number of 2. So 2 grams of hydrogen 2, if I know my chemistry, is 1 mole of that thing. So it's 1 mole of H2. And well, if I look at this pattern, 3 grams of H3 is equal to 1 mole of H3. So 1 mole of hydrogen and 1 mole of tritium, or rather 1 mole of deuterium and 1 mole of tritium, are obviously going to produce 1 mole of helium-4. So instead of 1 nucleus, or 1 particle of helium-4 being produced, 1 mole of helium-4 will be produced. And remember, we know how many particles or how many atoms there are in 1 mole. It's Avogadro's number. So the total energy will be the energy for 1 reaction multiplied by Avogadro's number, Na times delta E, that I calculated above. That's 6.02 times 10 to the power 23, Avogadro's number, times 2.82 times 10 to the minus 13 joules. This is a total energy of 1.7 times 10 to the power 12 joules. Now the number is looking quite massive. 1.7 to 2 significant figures times 10 to the power 12 joules of energy released, when all I need is 2 grams of deuterium and 3 grams of tritium. So if I could successfully fuse all of the 2 grams of deuterium, or 1 mole of deuterium to 1 mole of tritium, guess what? I get a pretty huge amount of energy being released. Even more so, gram for gram, than I would from nuclear fission. So fusion is a possible future energy source, and this question kind of gives us an indication as to why. And so we've answered questions here. This is the last question that I'll answer for today, but we've answered questions here that have tackled mostly the problems on binding energies per nucleons, per nucleon and I think binding energy in general, but we haven't really touched anything on the half-lives and radioactive decay and so on. So the next time I make a video, I will continue to answer the questions on nuclear physics, but I'll look at the questions specifically on half-lives, on radioactive decay, on activity, and those kinds of later in the topic questions. But I hope this video has been useful. Please leave a like, comment, subscribe. Let me know what other topics you would like to see. I'm going to be making these videos more regularly and trying to cover all of these paper 4 topics as soon as I can to get them all done before the exams in May. So that's all from me, Mr. K, for now. I'll see you again next time on Everything is Relative.